Hi, I'm Nikita, and I will tell you today about my work on contextual model types for algebraic effects and handlers, which is a joint work with my advisor, Alex Nanevsky. Algebraic effects are those effects in programming and programming languages that are defined by a set of operations that your programs might call. For example, we can model an effect of a single-cell integer state with two operations. One is get, to read an integer from that state, and one is set, to write a new integer into that. With these operations, we might write a program that, for example, increments the state, and it does so by first reading the current state value with get into x, and then later by setting a new state value, which is x plus 1, to our integer cell. And then it returns the previous state value. This previous state value is integer, and we type the program as integer. But moreover, what we typically want to know in programs that use algebraic effects is which operations they used. So we track their effects also in the typing alongside with the return type of integer. And we call such type systems that also track operations type and effect systems. And let's look closer at this type and effect system annotation. Those annotations actually and type and effect systems in general are currently an active area of research. There is a lot of papers published right now about type systems for algebraic effects. One common feature among them, though, is that all of them are treating effect information as a second-class citizen in the typing system, meaning that there is no direct way, no direct term in the language to add or remove or introduce or eliminate these effect annotations. They are collected implicitly from the term in a bottom-up fashion. In practice, this summer, people that made algebraic effects for OCaml published a paper about it. And in there, they also considered, well, what is the best type and effect system that we can choose right now for OCaml? But they noticed that actually they cannot choose yet an effect type and effect system for OCaml to track their algebraic effects, because there is not yet a type and effect system that would guarantee you the essential property of effect systems, that is effect safety. All your effects, if your type system tells you that there is no effect, then it's true. And effect safety is not something that current systems can guarantee yet in the presence of advanced features such as polymorphism, modularity, or generativity. And it is our idea that it is exactly because current type and effect systems treat effect annotations as second-class citizens and don't have terms to manipulate them in the language that this problem arises. So what we think is missing is exactly this ability to manipulate effect annotations directly. And so our idea is to move from a traditional type and effect annotation into a purely typing system and use something called a contextual model box type. It is a generalization of a simple box type that you might know from model logic, from linear temporal logic, which is also called necessity type, for example. And it is generalized by a variable context, where for us, actually, effect operations are variables. Note that it is not just a change of annotation. We actually change the language. We introduce constructors and destructors for this type, which also manipulate the effect annotation. We formalize our work in the system called ECMTT, which is an extension of contextual model type theory with algebraic effects. So what does it actually bring us to use model types? First of all, our typing system starts to manipulate effect annotations directly with introduction and elimination forms for effect scoping. Our operations become just bound variables in terms, and we can, for example, alpha rename them. And moreover, our operational semantics becomes super simple. Instead of many rules how to define handlers on your computations, we have just one, but I will show you. And the main insight that we obtained in doing this work that I want to communicate with you right now is that contextual model typing is actually the logic behind handling of algebraic effects. That was our big discovery. But let me go into detail and show you the language. So we have this model box type, and it is a box type generalized by a context. We call it psi in the slide. And the term to introduce this type is called also box, that now explicitly binds this context psi. For example, remember the Tinker program. Now, to make it into a box type, we say box get set, and then we repeat the Tinker program. By this way, we construct the model type. Note that this box must actually bind the full signature of effects. There is, if we say get and set, there is no other effect that we can use in that program. But let me show you. For example, if instead of a set we used raise, which is supposedly raising an exception, then our typing system would rule this program out, because raise is not under the box. Alright, but how do we actually use this type? And here is the elimination for it. It is a let form, and it works by binding the box type to a variable, a term of a box type, and then using this variable in another term. Note that it is just a variable rule, essentially. It gives you a variable. And it is actually very crucial for our semantics, because it is the only beta reduction that we have in our semantics. It is just beta reduction. It works by, well, reducing the box term to an actual box, taking the computation out of it, and substituting it for the variable. The way to use that variable is actually with handling. That's where handling comes into play. So handling for us is a variable rule. It applies not to a computation, but to a variable. And it is important because it allows us to keep the operational semantics simple. We don't have to define handlers on every clause of a computation. But let me show you an example of how handling works. So remember the Tinker program, we put a box around it so it becomes a box term of a box type. We eliminate it with letBox. We bind it to a variable u. Next thing we do is we apply handling to it. We use some handler for state and on that variable. Remember that the only beta reduction that we have is the letBox contraction. So that's the only thing we can do in this program. We cannot reduce handling right away. Let's do it. So the way the reduction works is that we take this computation of Tinker from under the box, and then we substitute it for the variable in the handling term. Handling then is defined as just a meta operation during a substitution. It's not a standalone thing. And we reduce it accordingly. We do the substitution, and it's a meta operation. And then it runs as defined by handler st, as you would expect. It all happens during a single beta reduction step. There is no separate reduction for handler. So what I showed you before was what we call local soundness, that we can distract our constructor or eliminate an introduction form, and we are in balance. Another side of that balance is local completeness or entity expansion, that we can take our term of a box type and expand it into a regex. We expand it into a letBox that binds it and then reboxes it and handles it. But here we use a very special handler, which we call identity handler. What it does, it explicitly propagates the effects from one effect context psi to itself. So, for example, if it was state, then what we would do is we would say that get maps to get and set maps to set. And it is very important for us because actually we can not implicitly leak effects otherwise. We must explicitly say how operations from the inside one theory map to another, to the outside. And that's where identity handlers come into play. And together, those two properties of local completeness and local soundness actually ensure that our design for our type of effect is modular and it is independent of other language features. So let me conclude for now and talk about what we actually achieved in this work. So we found out that contextual model typing is a natural fit for systems with algebraic effects, that it naturally describes handling, that handling is a manipulation with contextual model types. Contextual model types provide for us a direct control over effect scopes and effect annotations. They connect algebraic effects to model logic, which potentially allows us to transfer the results between the two fields. And let me give you an example of it right away. So currently, there is a lot of research into effect polymorphism, which is a polymorphism over effect theories. And in the slide, we show you an example that we adapted from a paper from the Popol 2019 that shows a problem with accidental handling of algebraic effects. We stated it in terms of model type systems, and we actually want to adopt a solution from model type systems because 10 years ago, Brigitte Pientka wrote a paper that wasn't about algebraic effects at all. It was about contextual model types. But we think that it was exactly the problem that currently algebraic effects researchers are solving. And we want to borrow that solution, and we think that it will be immediate solution to the problem of effect polymorphism, because for us it is a context polymorphism, but it had already been worked out. And you will find more details on that example in the paper. Another thing that we want to do is we want to develop Kripke semantics for our model effect types, which we will see entirely as propositions. We will switch from a language with terms to a language of only propositions that are standing for our effect types. So in a way, what we will get is we will consider the system of a logic for manipulating algebraic effects. We will replace our term judgments with judgments of validity, possibility, or truth, and we plan to develop Kripke semantics for it, which is something that is traditionally done for systems of model types or model logic. And by that, we will obtain immediately a Curry-Howard isomorphism between programming languages with algebraic effects and systems of model logic. But that's a future work. One more thing that we want to do in the future is to look into our equational theory. Because for us, right now, this modality of box psi behaves both as a monad and a comonad, which is peculiar, and we want to explore it. And the next big thing is dependent types. We think that we will have a good shot to getting to dependent types because, first of all, the work we base on, SymTT, was already lifted to dependent types and its development also. Moreover, we have enough features of the language that are simple, for example, simple operational semantics that will also simplify the lifting for us. And having dependent types will allow us to have equations between operations, which will describe how operations interact and will give us algebraic theories in our types instead of just signatures of operations. And that is it for me. Thank you.
Hello, virtual ICFP. I hope you're all having a wonderful conference so far. I am Mitchell Pickard. This is joint work with Graham Hutton. We're from the Functional Programming Lab at the University of Nottingham in the UK, and we're going to be showing you how to calculate a dependently typed compiler. Why would you want to calculate a dependently typed compiler? Well, compilers can go wrong. We all know that. It's not necessarily a very common occurrence, but we all enjoy formally verifying stuff. So it'd be nice to have completely formally verified compilers that we know cannot go wrong. Previous work by Hutton and Barr showed an alternative way of formally verifying a compiler. It doesn't, rather than writing a compiler and then formally verifying it, they show how to derive a compiler from the specification. So given a language specification, you can go through a calculation process, you get a compiler out of the other side, and then you also get a proof of the formal verification of the compiler for free. But their approach so far only deals with untyped languages. We want to show how to extend that approach to typed source and target languages. Our approach is based on the use of dependent types and is completely formalized in Agda, whereas the previous work is done in Haskell. The use of dependent types allows us to make sure that everything is completely type safe. So the compiler and the abstract machine are all type safe, which makes the resulting calculations a lot easier to mechanically check. So we're going to begin with a simple expression of natural numbers and Booleans. You've all seen similar things before, I'm sure. It's just a very basic expression type where we have natural numbers and Booleans. You can add natural numbers together and do if statements on Booleans. The problem with this is that you can construct illegal terms, such as trying to add true and 5. Obviously, a standard way of fixing this would be to write a type checker. But when we want to do calculations on these, it turns out to be easier to encode the typing information in the data type itself. So we're going to use an intrinsically typed representation in Agda. So this is where the dependent types come in. If you're not familiar with dependent types, this is where we index this expression by the type of the term it represents. So instead of just exp expression, it would be exp of bool or nat, for example. So the constructor for values gets collapsed into just one constructor. So whatever value this is, whether it's a nat or a bool, they can go through this constructor, and we will get an exp nat or an exp bool out of the other side. Add here specifies that we're not just taking expressions, we're taking expressions of natural numbers every time. So we take two natural number expressions in and return a natural number expression out. If takes a bool expression in, and that is the condition that we're going to work on, and it takes a true branch and a false branch, which must both be the same type, and then the return type is the same type as the branches. And this stops illegal terms type checking. You can't add together true and 5 now, for example, because this add has to take two natural number terms. And then we can write a simple evaluation function, which is going to be the specification of our language. This is how the language behaves, and we just take the exp of t, whatever type this is, and return a basic Agda type of t. So a value just gets collapsed into the value that's inside. An addition now, because we specified previously from the type of add that the two expressions have to be natural numbers expressions, once we evaluate this recursively, we know this is going to be a natural number. So we can add together these two natural numbers to get a natural number out the other side. And it's exactly the same thing with if. Because we have that proof of the types before, we can plug it straight into Agda's if then else function, and it will all just work. Our compilation target is going to be a stack-based abstract machine, but we want it to be completely well typed. So we use dependent types to keep track of the type of all the elements on the stack and what order they're in. So our stack data type is again indexed, this time by a list of types. This list will tell us the order and the type of all the elements on the stack. And now we construct this recursively just by starting with an empty stack and then an operator to push new elements onto the stack, which just updates this list by pushing the new type onto the head of the list. For example, the stack 5 on top of true on top of the empty stack, so that's just the stack with 5 and true on it, would have the type stack, and then a list of the natural number and Boolean, corresponding to the 5 and the true. So if we tried to construct a stack of this type with true here instead of 5, this would fail the type checker. So it knows at compile time what the type of all the elements is. The code type is similar. It is indexed, but this time it's indexed over 2 lists of types. The first list is going to be the type of the input stack. The second list is going to be the type of the output stack, because code will take an input stack, operate on the stack, and then return a new stack. So for example, some code to represent addition would have a type something like this. The first stack would have 2 natural numbers on the top, and the return stack would have 1 natural number, the 2 numbers added together. And then, because of this quantifier, we know that the rest of the stack is left unchanged. It can't change the rest of the stack. And now our compiler will take our expression type from before and convert it into some code. And the code simply takes a stack and pushes a new value on top of the stack, which is the value of this expression. And execution simply takes some code, and then, as you'd expect, takes the input stack, which corresponds to the input stack type here, and returns an output stack corresponding to the output stack type. Now, how do we know that the compiler we generate at the other end is going to be correct? So intuitively, we know that compiling an expression and then executing it should give you exactly the same result as just evaluating the expression directly using the evaluation function from before. And we can capture this in an actual compiler correctness condition. So this just formalizes what we've written above. So for some expression E, if we compile it and then execute it on some stack S, that is the same as evaluating it directly and then just pushing it onto the stack. Now, how are we actually going to do the calculation? So we have this correctness condition from before, and we want to solve this as an equation. We've got some unknowns here that we need to find. The unknowns in this case are the compiler, which is one of the key components we're calculating, the execution function, which will tell us how to execute the abstract machine, and the actual code type for the abstract machine. Previously, we only defined the type of it. As we go through the calculation, we're going to be defining new constructors for this code type. This whole calculation process is going to be performed by induction on E on our expression type, and we'll always start from this right-hand side. So we'll start from eval E on top of some stack S, and we want to turn it into a form that eventually is going to look like this left-hand side. We do that by starting to turn it into some form XXCS for some code C. So we'll have some code here executed on a stack. When we have that code, we can then create a new defining equation for compile. So we'll say that compile E, for whatever E we're doing in this induction case, is equal to the C that we calculated from before. This new defining equation will then allow this compiler correctness condition to be true, and it will tell us what the compiler is. And the calculation that we do to get to this point will be the proof of our compiler along the way, because it's based on the correctness. So I'll go through an example calculation now. This is going to be the simplest example possible in the interests of time. It's just going to be the base case for E equals val x. The other cases are explained in a lot more detail in the paper, so I do recommend you go and read that. As I said before, we start from the right-hand side. So in this case, it's eval of our E is now val x on top of some stack S. And we can simply apply the definition of eval from before. So this gives us x on top of some stack S. Now we're a little bit stuck. There's nowhere obvious to go from here, but we can remember that our aim is to rewrite this into the form XXCS. So we need to essentially solve this equation, which will allow us to rewrite the right-hand side into the left-hand side. And we can solve this because this C is existentially quantified. We can create a new code constructor here. So we're going to call it push because, as you'll see, it simply pushes a value onto the stack. But the important part here is that this constructor captures all of the free variables on the right-hand side. That means that this equation can then be used as a defining equation for exec. So not only are we defining this this new constructor, we are also defining an equation for exec. And in this case, the push constructor simply pushes this value onto the stack. Now that we have this new definition, we can use it in our calculation. And that gives us exec push xs, which is in the form that we were looking for before. Now we can create a new defining equation for compile by setting compiler valx equal to this bit of code, push x in this case, and this solves this specific case. Once we do that for all of the cases, we get this. So we create several different code constructors. Each of them have types that are nice and precise, thanks to the dependent types. And then we have our compiler and our execution functions. So that is the basic overview of all the methodology. Obviously, we skipped many steps. There are multiple other cases that we didn't cover, but the paper has all of the details. And then it also introduces a simplification of this method using code continuations, which lets us get rid of all of these appends. Finally, the paper demonstrates the technique on a more complicated source language that adds exceptions. These cause non-local control flow, where the stack doesn't just grow and shrink linearly, demonstrating that the technique works on more complicated examples. And again, it's all type safe. Even when exceptions are thrown, you know exactly what's going to happen to the stack. All of the Agda code, all of the paper is verified in Agda, and all of that code is available in the repository online, including another example calculation, which shows this technique applied to the simply typed lambda calculus. Thank you very much for listening to our talk, and I hope you enjoyed it, and I hope you go and read the paper. Enjoy the rest of your ICFP. Thank you very much.
Hi, Eddie. Good morning.
Hi, Harry. Good morning.
How are you doing?
Good, thanks. Are you enjoying ICFP?
Yeah, it's fun. I suppose this online format allows people to do interesting things. I like it.
Oh, wait. Now it's the time for us to present our paper, Reasoning about Effect Interaction by Fusion.
All right, let's get started. So do you remember what the paper's about?
Yes. So overall, our paper is about connecting two aspects of algebraic effects, their specifications and implementations. On the specification side, computational effects are specified by algebraic series, describing the signatures of primitive effect for operations, and effect series also come with a set of equational axioms, characterizing the behaviors of operations. On the implementation side, effect series are implemented by handlers, which provide models for effect operations in a way respecting the equational axioms.
This is a classical instance of separating an implementation from specification, isn't it? Where a programmer writes programs and reasons about them according to the effect theories, which are separately implemented by handlers.
Indeed. And even nicer, both effect series and handlers are composable in their own right. Given two effect series, you can combine them into a bigger series containing all operations from the subseries, and possibly adding some new equations to specify the interaction of operations from different subseries. On the other hand, handlers are also composable by sequential composition. Given two handlers, they can be applied one by one to handle operations in a computation.
Well, that sounds really nice. So what's the problem here? I don't really remember the details of the paper.
The problem here is that there's a missing link between the compilations of effect series and the composition of effect handlers. It's quite interesting you don't remember what our paper is about, because it is motivated by a program session started by you.
By me? So, Eddie, are you around? I'm looking at some fun stuff.
Yep, what's it?
I've been looking at effect handlers lately, and I'm trying to write a little program solving a SAT problem using effect handlers.
Sounds cool. I've heard of equational series of effects. Can you tell me more about effect handlers and your program?
Yeah, sure. Actually, I'm a bit stuck with the program, so let's take a look together. First, the code HST on the right-hand side of this slide is a standard handler for the effect of mutable state using state parsing functions, implementing two operations get and put that reads or writes the mutable state respectively.
Yep, and there's a series of mutable state, which has a number of iterative equations specifying the behaviors of put and get. For example, like the one on the left side of the slide, saying that writing S into the state and immediately reading the state results in S. Does your handler respect this theory?
Yes, I've checked my handler respects all the equations of the standard theory of state.
That's nice. But then how do you use this handler?
Well, handlers can be applied to programs invoking effectful operations, such as this program, append, which reads the state and then appends one more element to the state. Then, the handler HST can be applied to it, transforming it into a state parsing function. What's cool about handlers is that a lot of the language features can be implemented as handlers. For another example, the non-deterministic choice operator in logical programming can be implemented as the handler HND, which models non-deterministic computations as lists of results.
Yeah, and I also think your handler respects the usual axioms of non-determinism, such as associativity, since operations are lists respect them.
Yeah, that's right.
And can you show me a use case of this handler?
Sure. Check out this little program, choose, which picks one element from a list non-deterministically using the OR and fail operations. Using this, we can write the program searching for Pythagorean triples, as well as do logic programming in it, like just as in Prolog. Applying the handler HND to this program then produces a list of all possible results. The best part of algebraic effects and handlers is that they can be easily composed. I told you earlier, I'm writing a program solving the SAT problem using state and non-determinism, and this is the program. A formula represented as a function taking a list of Booleans to a Boolean, and solve tries to find n Booleans, making the formula true. It's basically a trivial search algorithm. The currently selected Booleans are stored in the mutable state, and at each step, a Boolean, true or false, is picked non-deterministically and appended to the state.
Wow, this is cool. But you said you are stuck at this program. What's the problem here? it seems to work very well.
Right, the program is fine. What puzzles me is the order of applying handlers to the program. We can either apply the handler for non-determinism first, or the handler for mutable state first. But I was surprised that only one of them gives the correct answer. And for this particular program, I can expand out the program after handling and check which one is correct. But it is already tedious and tricky for the small program, so I'm worried about trying to determine the order of composing handlers in general for larger programs.
I see. Let me have a think. I guess the way out is thinking about equations again. So when you wrote your set-solving program, you were expecting the equational axiom of state and non-determinism we talked about earlier to still hold, right?
Yeah, I did.
And did you assume some more equations characterizing the interaction of state and non-determinism for your program to work?
I think I also assumed non-deterministic operations and state operations are commutative, in the sense that two adjacent state and non-determinism operations can be swapped without changing the meaning of the program. For example, my solve program assumed reading the state before and after a non-deterministic choice is equivalent, which intuitively means that different non-deterministic branches have independent state.
I see. I think this explains why only one particular order of composing the handlers of state and non-determinism works for your solve program. Since your program assumes the commutative laws, technically you are assuming the tensor of non-determinism and state. You need to make sure your composite handler indeed respects these laws, just like you show your handlers HND and HST respect their series.
I see. Well, I totally agree with what you said, but it still seems like a tricky job to do. You know, semantically, the with handle construct is a fold on the syntax tree of programs, so the composite handler is a composite of two folds. It would be quite laborious to directly verify the composite handler respects the laws of interaction.
Indeed.
Wait, I've got an idea. Since handling is semantically a fold, some techniques from the program calculation community may be useful. They're very good at working with folds. In particular, I'm thinking about fold fusion. In this context, it means that if we can find some handler, call it HND diamond HST, such that handling with HND composed with handling with HST is equivalent to handling with this fused handler, then we can reason about the fused handler as a surrogate. The point is verifying that the fused handler respects an equation is relatively easy, and it implements that that handling with the fused handler respects the equation too, since the with handle construct is a model homomorphism of the effect theory.
Right. And then handling the fused handler is equivalent to the composite handler. It sounds a good idea, but it's not immediately clear to me how to define your diamond operator for fusing handlers.
Well, my friends Nick and Tom had a paper on optimizing effect handling by fusing handlers. I think we can tailor their technique to meet our needs. It's slightly involved to fully explain the technique, but roughly speaking, the idea is that when the first handler H1 encounters an operation that is meant to be handled by the other handler H2, then H1 doesn't need to leave the operation in the syntax tree of the computation, and instead, it can directly handle this operation using H2.
I believe it is intuitively the right thing to do, but is it really technically sound?
Well, not in general. But it can be fixed by restricting handlers to be modular handlers, which are handlers that work independently of each other. The precise definition of modular handlers is also slightly involved, but the intuition is that they exploit parametricity to guarantee that a handler doesn't mess around with operations that are meant to be handled by this handler.
I see. But there's one more serious problem. When H1 says an operation meant to be handled by H2, I don't see how you can use the clauses of H2 to handle this operation. Simply because the carrier of H2 is not computed yet, right? It is only computed after H1 finishes.
Well, that's true. But I think this can be fixed by the classic CPS transformation trick. Since the carrier of the second handler will be computed eventually after H1 finishes, you can make the first handler H1 work on a continuation monad where the carrier of H2 is the final result type. Then, whenever H1 encounters an operation meant to be handled by H2, the operation can be handled by acting on the result type of the continuation monad. This sounds a bit of a mouthful, but it's essentially the same technique as Andrei Filinsky's CPS-based implementation of monadic reflection.
Cool, but it's a lot of information. I think we can write a paper about it.
a good idea. So thanks, Eddie, for reminding me that, why we're speaking at ICFP. Is that really how we came up with this paper? Well, never mind. As we explained, in this paper, we reasoned about composite handlers by fusing two handlers into a single, more powerful one, just like two fighters can be fused into a more powerful one in the anime Dragon Ball Z. In the paper, we show for any two handlers H1 and H2, provided they are modular, which roughly means that they don't mess around with the operations that aren't meant to be handled by them, we can handle them into a single handler. We can fuse them into a single handler, such that handling with the fused handler is equivalent to the sequential composition of handling with H1 and H2.
With this fusion theorem, we can show a number of results relating the combinations of effect series and the sequential composition of handlers. The first one here says that all equations respected by handlers H1 and H2 respectively are still respected by their composite handler. In other words, if H1 respects a series T1 and H2 respects a series T2, then the sequential composition of H1 and H2 respects the sum of T1 and T2, which is simply the combination of T1 and T2 without any new interaction equations. But here you have to be careful. This only holds for modular handlers, and it's possible to construct counterexamples if H1 and H2 are not required to be modular. Moreover, if effect series are combined with some interaction equations, we show some sufficient conditions for the sequential composite of two handlers to respect the interaction equations. So for the motivating example we talked about earlier, both the handlers for state and non-determinism are modular handlers. Thus, we immediately know the composite handler respects all the equations from the theory of state and non-determinism because HST and HND respects them. And the result in this paper tells us for the composite handler to respect the commutativity equations of stateful and non-deterministic operations, it is sufficient to show this equality holds for each operation of state and non-determinism. Although this condition looks maybe a bit scary, it is actually simpler to work with than directly proving from the definitions, because this condition involves only the clauses of relevant operations of the two handlers, rather than recursive folds on syntax trees. For example, the clause for put is this simple function, and the clause for or is this simple function, and to show put and or are commutative under the composite handler, it is sufficient to show this equality. The equality is actually very easy to show. Expanding the definition of cput, we get this. And with some simplification, we get this. And again, using the definition of cput, we have the needed equality. And the point here is that proving a composite handler satisfies an interaction equation in this way is much easier than a direct proof from the definitions. And there are also some more case studies in the paper, which you may find interesting. For example, we show that with the standard handler of state of stateful operations, get and put, are always commutative with any operations handled after the state handler. This is a generalization of the running example we've just seen. So these are basically what we have in the paper. And if you are interested in the interaction of effect series and their connection to handlers, or if you are interested in fusing handlers together for efficiency, which is a topic we didn't expand in the paper, but our fusion operator is certainly useful for, welcome to check out our paper. Thanks for listening.
Yeah, thanks.
Hello, I am Zoe Paraskeva-Bulu, and I will present the paper Compositional Optimizations for Certicox. This is joint work with John Lee and Andrew Appel. This paper is about a new lightweight technique for compositional compiler correctness. We show how we can use existing compiler correctness techniques to obtain a compositional compiler correctness theorem that allows us to link together programs compiled with different compiler configurations. We apply this technique to compositionally verify the optimizing Midland pipeline of the Certicox compiler, a compiler from Cox's specification language Galena to C. With this compositional theorem, we can obtain a linking theorem for the Certicox compiler that allows us to compile programs with different optimizations enabled. This is useful as not all optimizations are beneficial for all programs. We may also want to add new optimizations or reorder existing optimizations and link with code compiled with previous compiler configurations. The key is that the specification of the pipeline remains the same regardless of the particular optimizations that are used, and this is exactly what we need to have a compositional compiler correctness theorem. In the rest of the talk, I will describe how we can achieve such a compositional compiler correctness theorem using existing compiler correctness techniques. Generally, to verify the correctness of a compiler, we prove that when a whole program is compiled for the compiler, the behavior of the target program refines the behavior of the source. This specification asserts that every behavior of the compiled program, P bar, is a valid behavior of the source program, P. But in this specification, we have assumed that the source program is a closed, standalone program. This is hardly ever the case, as most of the real-world programs consist of components that are compiled separately and link at the target level. More realistically, we want to be able to compile different program components with different compilers that are verified independently, and be able to say that the behavior of the whole target program, which is obtained by linking the individual target components, refines the behavior of the source program, which is obtained by linking the source components. But this is a hard problem, and there has been a lot of research in the past years to devise techniques for compositional compiler correctness. There are few solutions in the literature that can be applied to higher-order functional languages. Each of them offers different compositionality guarantees and requires a different amount of sophistication. On one end of the spectrum, we have separate comsert, that uses a very lightweight technique to verify separate compilation. This technique requires only small adjustments to whole program verification, but it is not compositional. Programs can only be compiled with the same compiler, except perhaps some optional same language transformations. As we move across the spectrum, we have Pilsner, which is proof correct using pils, a novel relation that provides strong compositionality guarantees and support verification of entirely different compilers between the same source and target languages. But pils is a much more complicated technique than standard compiler correctness techniques. Even further up the spectrum, we have verification using multi-language semantics that can be used to reason about linking of programs compiled from different languages. But this requires setting up a multi-language that embeds the source, target, and intermediate languages. We see that as we move across the spectrum, the proof techniques become more sophisticated and they require much more effort than standard techniques used in whole program compiler correctness. Our solution supports compilation with different compilers between the same source and target languages. We demonstrated by imposing the additional restriction that compilers go through the same sequence of intermediate languages. We can use existing compiler correctness techniques, in particular logical relations, to obtain a compositional compiler correctness theorem. So why is the problem of compositional compiler correctness so hard? Say that we have a multipass compiler comprised of a number of passes that are independently proved to satisfy behavioral refinement. Typically, behavioral refinement is transitive. Therefore, we can derive that the whole compiler satisfies behavioral refinement. However, behavioral refinement is not compatible with linking. So the behavioral refinement specification cannot be extended to separate compilation. So what is linking compatibility? We say that the relation R is compatible with linking if, when a source program relates to a target program, and a second source program relates to another target program, then the whole source program obtained by linking the source programs relates to the whole program obtained by linking the target programs. Therefore, when two compilers are approved to satisfy R, we can compile programs separately through these compilers and obtain that linking such programs in the source and target also satisfy R. But what is this R relation? To specify the compiler, we must pick a relation that implies the top-level behavioral refinement that we are interested in proving. This property is called adjacency. In addition, for the specification to be compositional, this relation must be compatible with linking. Logical relations are a widely used proof technique that are used, among other things, to prove program equivalence and refinement. One of the strengths of logical relations is that they are both adequate and compatible with linking. Sadly, logical relations are not transitive. In particular, say that we have a compiler that goes through languages L1 to Ln+1 with n transformations, and that we have proved each transformation correct using a logical relation between the source and target languages of transformation. We would like to specify the compiler with a logical relation between the source and target languages of the compiler. But generally, it is not provable that the composition of the individual logical relations that are used in the correctness of each transformation implies the top-level logical relation. So there is no obvious relation that we can use to specify the whole compiler. In this paper, we make the crucial observation that adequacy and compatibility with linking are closed under relation composition. That is, we can use the composition of the individual logical relations to give a compositional specification for the compiler that implies behavioral refinement. Hence, we do not need transitivity to obtain an end-to-end relation. That means that if we have two compilers that satisfy the relation obtained by composing adjacent logical relations, we can obtain the top-level linking theorem that we are interested in. So what is the catch? This relation depends on the intermediate representations that are used in the pipeline. Therefore, it can only be used to specify compilers that have the exact same sequence of intermediate languages. I will now show how this technique can accommodate same-language transformations. In the previous pictures, we implicitly assumed that there are transformations only between the intermediate languages of the compiler. But compilers often have same-language transformations on some intermediate languages. In this picture, for example, we have a series of same-language transformations on language L2 that are verified with the same language logical relation RL2L2. Note that the sequence of such transformations trivially satisfy the transitive closure of RL2L2, RL2L2+. Because same-language logical relations are typically reflexive, the transitive closure of RL2L2 is satisfied by 0 or any other arbitrary number of L2 transformations. Therefore, by interleaving the transitive closure of a same-language logical relation between cross-language logical relations, we can facilitate any number of same-language transformations on its language level. If you look at our paper, you will also learn about a new technique that allows proving divergence preservation of transformations using logical relations. Let me now return to the application of this technique to the verification of the Certicox compiler, a compiler from Cox specification language Galena to C. We use this technique to compositionally verify the optimizing middle and pipeline of Certicox, and we prove a linking theorem that supports separate compilation with different optimizations enabled. Certicox Pipeline starts from Galena and uses Metacox to reify Galena into its abstract syntax tree representation in Galena and to erase proofs and types. Then, after some code simplifications, it translates the code to Lambda ANF, Certicox core intermediate representation based on a normal form. It does so either with a direct or a continuation passing style transformation. Then there is a multipass optimizing pipeline that translates the code to lambda ANFC, a subset of the lambda ANF language without nested functions. Lambda ANFC is a low-level representation that does not have closures, and therefore it can be code-generated easily to a first-order low-level language. Certicox backend generates C code that can be then compiled correctly with a ComCert-verified compiler. The lambda ANF pipeline of Certicox consists of 7 distinct transformations. Some of them are repeated multiple times across the pipeline. These transformations optimize the code and move to a representation without closures. I will not explain this transformation in detail in this talk, but you can read our paper to find out more about them. Notably, we describe new selective strategies for lambda lifting to achieve modular and efficient closure allocation. All of the lambda ANF transformations, except from closure conversion, are same language transformations but do not change the representation of values. But closure conversions change the representation of closures from closure values to explicitly constructed closures. Therefore, closure conversion behaves like a cross-language transformation. In order to verify the pipeline, we use 2 logical relations. A reflexive same-language logical relation E that is used in all transformations except from closure conversion, and a cross-representation logical relation ECC that is used to prove correct closure conversion. The chunks of transformations before and after closure conversion satisfy E+, the transitive closure of it. Therefore, the top-level relation that is satisfied by the whole pipeline is E+, composed with ECC, composed with E+ again. This top-level relation is satisfied by any sequence of lambda ANF transformation that encompasses a closure conversion transformation. We can therefore easily add new same-language optimizations before and after closure conversion and prove them correct with the E relation. Or even add a new closure conversion transformation that, for example, uses different closure environment representations, as the ECC relation makes no assumptions about the closure environment representation. The end-to-end pipeline will still satisfy the same end-to-end relation. At the top level, we obtain a linking theorem for Certicox that states that programs can be compiled separately through Certicox with any configuration of the optimizing lambda ANF pipeline. So to summarize, we present a novel lightweight technique for compositional compiler correctness that we use to obtain a compositional compiler correctness theorem for the Certicox compiler. The key idea is that we introduce is that we do not need transitivity to obtain a top-level compositional relation for a multipass pipeline as long as we are willing to accept the restriction that compilers go through the same sequence of intermediate languages. This technique is compatible with standard logical relations or any other relation that is adequate and compatible with linking. Certicox is open source and available at GitHub, where you can download and install it. Thank you for watching this talk.
Hello everyone, I'm Ningning. Today I'm going to talk about generalized evidence parsing for effect handlers, or efficient compilation of effect handlers to C. In this work, we gave a formalized evaluation semantics from algebraic effects into a polymorphic lambda calculus, and show how this technique can be used to generate efficient C code with no special runtime support. We achieve our goal using a sequence of refinements to the semantics of algebraic effects. Through multi-prompt delimited control, evidence passing semantics, bubbling yields, and a monadic translation. And we prove each step is semantics preserving. Along the way, we also explore various interesting points in the design space. We have implemented our techniques in the Coca programming language, which compiles to standard C code without needing any special runtime support, not even a garbage collector, thanks to precious reference counting techniques. We show our technique is effective by benchmarking Coca against the other implementations of effect handlers. The main two challenges in this work is how to search through the evaluation context efficiently and how to capture the assumptions efficiently. Let's look at a concrete example. Here is an example for the reader effect. There are three parts. In the first part, we define an effect read, which has a single operation ask that given a unit returns an int. The second part defines a handler for the read. The implementation says that if the program calls an ask, it will resume the resumption k with the result value 1. Handler takes a computation, which is represented as a unit taking function. In this computation, we simply call ask twice. Since each ask returns 1, we will get 2 as our final result. Reader is one of the simplest examples for algebraic effects. But in practice, we can also have more complex examples where we can never resume, as in exceptions, or resume multiple times, as in non-deterministic programs. This page gives the essence of the untyped semantics of algebraic effects. But please don't get scared. While being formal, the operational semantics is quite intuitive, and we will go through the rules one by one. The first rule is just the standard call by value beta reduction. The handler rule is where we define a handler. As we have seen, the computation to be handled is always a unit taking function, which essentially corresponds to a suspended computation. We execute the computation and it turns a handler into a handle. When handling a computation, there are two possible situations. In the first case, the computation evaluates to a value, so we remove the handle and propagate the value. In the second case, the computation performs an operation which is handled by a handler. Several things to note here. First, this capital E represents an evaluation context, which essentially represents a code stack. That means we can perform an operation deep inside the code stack. Then, how do we know which handler is used to handle this operation? We will need to search through the evaluation context and find the innermost handler that can handle this operation. And we get the operation implementation F. Now we are ready to apply F to the operation argument V as well as a resumption, which captures the whole evaluation context between handle and the operation code. It seems everything just works well until you want to compile algebraic effects efficiently. The main problematic rule is perform, which includes two potentially expensive runtime operations. First, since the perform can be deeply inside the evaluation context, and we require H to be the innermost handler. That means we need to perform a linear search through the current evaluation context. Second, after finding the handler clause F, we need to provide the resumption. And that means we need to capture the evaluation context up to the find handler and create a resumption function. This is not only expensive, but might be impossible for some platforms like .NET or Wasm, where you have no access to stacks. In this work, we address these compilation challenges by representing various refinements to algebraic effects. Next, we will explain each of these steps, and we will use this progress bar to keep track of where we are. We start by looking at the reader example again. but this time through the operational semantics. First, we put the definition of the handler on the top right and fit the program into one line. When evaluate the expression according to handler, we are going to execute the computation. And by app, we just substitute the unit away and get a handle expression. Now we evaluate the first perform. We need to find the innermost handler, in this case h1. So we evaluate the expression into f, applied to the argument unit and the resumption. F says it's going to apply its second argument to 1, which further gives us this. As the second perform ask will be handled in a similar manner, the final result would be 1 plus 1, which is 2. To pave the way, we first apply multi-prompt semantics. We omit some less interesting details. With multi-prompt semantics, each handle is replaced by a prompt. Importantly, each prompt is associated with a fresh unique marker, in this case M1. Now, when we do perform ask, we can search through the context and evaluate perform to yield M1 as we know exactly which handler to yield to. We can also apply the operation implementation to the argument, and it now only waits for the resumption K. Now, prompt will handle yield, where we will capture the resumption and evaluate to the same expression as before, except we have replaced the handle with prompt. At first sight, going through multi-prompt semantics does not seem to buy us much, because the overall process is still the same. However, now we separated searching from capturing, and it opens up the way for optimizing each part individually, which we will do with evidence parsing and bubbling. First, we avoid searching using evidence parsing semantics, where instead of searching for a handler in the evaluation context, we will push down the current handlers as an evidence vector. To illustrate the idea, we need a little bit more space between expressions. Evaluation always starts with an empty evidence vector, but after handler evaluates to prompt, it inserts itself into the evidence vector for the rest of the computation. Now we have an evidence for read. At this point, the first perform ask can directly get the current evidence vector, look up the evidence for read, which gives us M1 and H1, and we can directly generate yield M1. And this is the essence of evidence parsing. Importantly, such a lookup can even be implemented efficiently in constant time. In particular, if the system is equipped with effect types, as in the case of COCA, then the effect type will correspond exactly to the runtime shape of the evidence vector. And if we know the effect type at compile time, we can statically determine the index of a handler. We can even do more. It turns out with evidence parsing, we can often avoid yields by evaluating tail resumptive operations in place. Tail resumptive operations are of this form, where the resumption is directly resumed with an expression E. For example, f in H1 is of this form. Well, this is not accidental. Almost all common operations used in practice are tail resumptive. For those operations, once we yield up, we will immediately resume with the result of evaluating E. But that's not necessary. We can directly evaluate E in place. In this case, since we can get H1 from the evidence vector, we can replace this yield M1 with the tail resumptive body, in this case 1. We will do the same for the second perform, so we will be able to evaluate the whole expression without even doing any yields. One subtlety of this optimization, though, is that we will need an underframe to adjust the evidence vector to preserve semantic correctness, but we are going to skip the details. However, not all operations are tail resumptive. For example, if f is of this form, then we will get back to yield, and yield is still a non-local and expensive operation. We use bubbling to make yields local by bubbling a yield up until it meets its corresponding prompt frame. To see the idea of bubbling more clearly, let's first make the call stack more obvious. For example, in the third expression, we will first do yield, whose result will be added to perform ask, and the whole computation is guarded by a prompt. We can also do the same to the resumption. Now it is more obvious that during capturing, we are capturing multiple frames at the same time. With bubbling, we are going to bubble up the continuation in little parts. When we are yielding, we keep the currently partially built up resumption as an extra argument to yield, starting from the identity function. We extend it with every frame one at a time until we meet the prompt where the resumption is now complete. Now with evidence parsing semantics, we have made perform local, and with bubbling, we have made yields local. Since everything is local, it opens up a way to implement everything in a monad. With monadic translation, our running example will be translated into a monadic expression as this. The monad we are using is also regular. It is essentially a reader monad for the current evidence vector composed with a control monad. The definition of control monad can be better understood via the monadic binding of mon. If we bind E with G, we will first evaluate E. If E results in a pure result, then we can pass the result and the current evidence vector to G. Otherwise, if E performs an operation and thus generates a yield, we will bubble this yield and add G to the partially built up resumption. You can see all ingredients of transitions in this definition. We have evidence parsing, multi-prompt delimiter control, and bubbling. At this point, we can use regular compilation techniques to compile the algebraic effects to any target platform. As an example, we show how Coca compiles to standard C. This is the C code generated for this expression, and we highlight some key components. This context is the evidence parsing part, which stores the current evidence vector. When perform ask, as in this case, the type is statically known, we can do a constant time array access to find the handler. We also optimize the representation of the control monad, since in practice, most operations are tail resumptive. We assume most code will not yield. So we always return results normally assuming pure and set a flag to indicate yielding. If yielding, we will perform a yield extend, which implements bubbling. As you can see, all ingredients fit nicely into the final generated C. Most importantly, if the code does not yield, as in most cases, the computation will take the happy path, where there is no yield and no allocation. All the techniques we have described are implemented in the Coca compiler, and we benchmark Coca with other implementations of effect handlers. The results are made to establish that our work is viable and can be competitive, but should not be interpreted as a measure of absolute performance between systems and languages. Our paper included more detailed discussion of the benchmarks. Here, we would like to highlight that the counter benchmark emphasizes the impact of nested handlers. As we can see, when the number of nested handlers increase, as the operation is tail resumptive, the time of Coca stays nearly the same, where, for example, for multi-core or camel, the time increases linearly. Hope you enjoyed this presentation. If you are excited to know more, please play with Coca. On Thursday, we are going to give a tutorial on Coca. Please come and join us if that sounds interesting to you. Finally, we have also implemented our technique as a Haskell library available on Hackage. That's all I want to say. Thank you for your attention, and we are happy to take any questions.
Hi everyone, I'm John, and I'll be presenting our work on deriving efficient program transformations from rewrite rules. Compilers are very difficult to write without bugs, so lately people have taken to writing compilers along with mechanized proofs of their correctness. This is very effective at squashing bugs, but mechanized proofs can be extremely tedious to do. We've been building a verified compiler called Certicox, which goes from Galena, the core language of the Coq proof assistant, to a subset of C. Certicox backend has a number of optimization passes, each of which must be proved correct, and these proofs can take up a lot of our time. For example, this uncurrying pass is implemented in 300 lines of pretty straightforward Coq code, and then took me the better part of a semester and 2,000 lines of Coq tactics to prove correct. As another example, this shrink reduction pass was first invented and used in 1997, but wasn't proved correct, not even on paper, until 2016. So, it's natural to wonder whether automation can help make it easier to write these kinds of verified program transformations. While building Certicox, we noticed that a lot of proofs about program transformations seem to have the same two-layered structure. First, a functional program implementing the transformation is proved sound with respect to some relational specification, usually given in the form of syntactic rewrite rules. Then, this relational spec is proved sound with respect to the semantics of the object language. This way of structuring the proof cleanly separates the task of proving a program transformation correct into one part that can just think about the semantics of the object language, and one part that can just think about the various data structures and invariants that need to be maintained by the implementation. Prior work has focused mostly on building tools which can take in relational specifications, automatically check that they are semantically sound, and then automatically generate reasonably efficient implementations. But these tools usually don't give the user control over low-level details that are important for efficiency, such as exactly what kinds of helper data structures should be used to store and compute data flow facts. In this work, we try and bring some of this control back to the user. We do this by building a tool which takes in not only a relational specification in the form of a set of rewrite rules, but also descriptions of exactly which kinds of helper data structures the user would like to use to execute those rules in an efficient way. Our tool generates from these descriptions large parts of a functional program and its correctness proof, leaving behind holes for the user to fill in manually with code that explains how each of their selected helper data structures ought to be manipulated. This generated partial program is given a rich dependent type, which ensures that once all holes are filled with well-typed terms, the program that you get out is guaranteed to be correct with respect to the specified rewriting relation. In order to build this tool, we had to figure out how to formally specify the various kinds of helper data structures often used by compiler writers in their implementations. And what we found is that a lot of these data structures maintain invariants of a very specific form, which I'll illustrate now with a concrete example. Consider the following toy object language, containing let bindings and an if-then-else construct that scrutinizes variables. And suppose we're writing an optimizer that can perform these two transformations. A case-folding transformation that folds if-then-else expressions down to the proper branch if we know that the variable being scrutinized is bound to a Boolean literal, and a dead variable elimination transformation that removes let bindings for unused variables. Each of these transformations requires its own custom helper data structure in order to be implemented efficiently. In the case of case folding, we can pass around an extra parameter, which we call env, that maps variable names in scope to the Boolean literals that they're bound to. When we encounter a let binding for a variable to a Boolean literal, we can extend env accordingly before making a recursive call. Then, when we encounter an if-then-else that scrutinizes a variable x, we can look up x in the environment to check if it's bound to a Boolean literal. And if it is, we can perform case folding. To implement dead variable elimination, we can maintain a piece of state which maps variable names to the number of times that variable is used in the expression being transformed. Then, when we hit a let binding, binding a variable x, we can check if that variable is dead by checking if it has 0 uses. Here's an example which illustrates how these implementation strategies can be used to optimize the term shown on the left. To start, the environment is empty, and uses maps each variable that occurs in the term to the number of times it's used. In this case, there are 7 variables, x, y, z, a, b, c, and d, and each is used once. The first thing we encounter is a let binding from y to true. So we add this binding to the environment and make a recursive call. At the recursive call, we encounter a let binding for z, which we can then add to the environment and make a recursive call on the if-then-else. Now we look up x in the environment to see if we can perform case folding. In this case, x is not in the environment, and so we can't perform case folding, and instead just make recursive calls on each of the branches. In the recursive call on the then branch, we encounter an if-then-else scrutinizing y. When we look up y in the environment, we find that it's bound to true, which means that we can fold this entire if-then-else down to its then branch. In doing so, we'll be deleting occurrences of variables b and y, and so their use counts will have to be decremented from 1 to 0. Something similar occurs in the recursive call on the else branch. We encounter an if-then-else scrutinizing z, and when we look up z in the environment, we find that it's bound to false. So we can perform case folding, replacing this if-then-else by its else branch d. In doing so, we'll be deleting occurrences of variables z and c, and so we have to decrement their use counts. Now, after decrementing various use counts, certain variables are dead, and we will discover this as we return from recursive calls on the way back up. Notice that at each step in this example, there was a subterm in focus, which I rendered in black font, and a surrounding context, which I rendered in gray. We can think of an implementation of a program transformation as a state machine with configurations of this form, consisting of pairs containing surrounding contexts and subterms in focus. From this perspective, data structures like env and uses maintain invariants which relate their values to these machine configurations at each step. For example, the invariant on env is that every key value pair xb corresponds to the variable name x being bound to Boolean literal b in the surrounding context c, and the invariant on uses is that every key value pair xn corresponds to the variable x being used n times in c applied to e, that is, the entire term being optimized. So, going back to this picture from earlier, we now have our answer to this question of how to specify the invariants held by data structures that compiler writers like to use. And our answer is that a lot of these data structures maintain invariants that relate their values to pairs consisting of a one-whole context and a subterm in focus. In addition to this notion of helper data structures, our tool also supports a restricted kind of delayed computation and the ability to specify custom termination metrics. The resulting framework is simple but capable of expressing many of Certicox backend passes. Here in green, I've highlighted the passes that we've implemented using our tool, in blue the passes that we believe could be implemented, and in red the one pass, closure conversion, which we believe is not expressible, mainly because it's rather tricky to figure out how to express closure conversion as a rewrite rule. Now, to give a sense for what it's like to use our tool, I went ahead and implemented the example that I described on the previous slides in Coq. So, to use our tool to write a proved correct program transformation, the user first has to define the syntax of the terms of their object language. This can be done in the normal way by encoding the syntax in a Coq inductive type, which I've chosen to call exp. Then, the user runs a metaprogram, which we've written using metacoq, a metaprogramming library for Coq, and this metaprogram parses their inductive definition and automatically generates a type of one-whole contexts for terms of their object language. Using these definitions, the user can then define the rewrite rules that they would like to implement, again in the usual way by defining a Coq inductive relation. In this case, I've chosen to call this relation rewrite step, and each constructor of rewrite step corresponds to a rewrite rule that I would like to implement. Next, the user defines the helper data structures that they would like to use along with their invariants. Here there are two helper data structures, an env map mapping variable names to Boolean literals, with the invariant that every key value pair corresponds to a known let binding in the context, and a uses map mapping variable names to natural numbers, with the invariant that getting a use count from the uses map gives back the number of times that variable is used in the expression being optimized. In order to actually use these helper data structures, our tool demands that the user prove the following three theorems, which basically explain to the tool how the invariants on the user's helper data structures can be maintained at each recursive call. In this case, here is what the proofs of these three theorems look like. Now, skipping over about 200 lines of boring proofs about use counts, we're finally ready to start deriving a proved correct implementation. The user begins by declaring a value, in this case called optimize, with the type of proved correct rewriters. This type is parameterized by various pieces of the specifications presented on the previous slides. The user invokes our tool by using the tactic makeRW. This tactic parses the specifications given in the types and generates large parts of a functional program and its correctness proof. The tactic leaves behind a number of proof obligations, each corresponding to a hole that must be filled in by hand. In this case, there are 8 proof obligations, 6 of which correspond to proving things about termination and to delayed computations, which we don't use. So, these obligations can be easily solved by a couple lines of cock tactics shown here. After running these tactics, what remain are the following 2 proof obligations. This first proof obligation is basically the tool's way of asking the user to explain how to implement the case folding transformation using the helper data structures that they specified. This hole is given a fancy dependent type, which prevents the user from filling it with an incorrect implementation. Similarly, the second goal is the tool's way of asking the user to explain how to implement dead variable elimination, and again, the types prevent the user from making a mistake. In each case, the user fills the hole by using tactics, which generate cock code to implement the corresponding rewrite rule, and then prove that code correct. Here's what the tactic looks like for implementing and proving case folding correct, and here's the tactic for implementing and proving correct dead variable elimination. After running these tactics, 0 proof obligations remain, and the user obtains an implementation of the desired program transformation, proved correct with respect to a set of syntactic rewrite rules in cock. To evaluate our tool, we compared the number of lines of code and proof it took to implement the transformations highlighted in green using our tool compared to doing it all by hand. Then, we measured the runtimes of some of these generated implementations on a suite of benchmarks, and once again compared to handwritten counterparts. Here are the line counts. In blue are the amount of lines of code and proof it took to do everything by hand, and in red are the amount of lines of code and proof it took using our tool. As you can see, our tool in some cases significantly reduces the amount of manual proof effort required. Here are the runtimes, which basically show that our generated implementations are about as fast as their handwritten counterparts. Quick disclaimer here, there are a lot of details that I'm not going into in this comparison, and if you're curious about those details, please feel free to check out the relevant section of the paper. So, what's next? Currently, our tool generates very dependently typed cock recursive functions written in a kind of continuation passing style to make sure that the generated code will be extracted to efficient OCaml. This is great for efficiency, but makes it very difficult to reason about the code that our tool generates inside cock. So, in future versions of our tool, we would like to make sure that the generated cock code is more human readable. We would also like to investigate whether it would be possible to use our tool to write cross-language transformations, such as CPS, ANF, and closure conversion, and we would like to try implementing more of the transformations in Certicox backend using our tool. Thanks for watching.
Hi, my name is Ushin Kidney, and this is the presentation for the paper Algebras for Weighted Search, a joint work between myself and Nicholas Wu. This is a paper about search algorithms, and modeling those algorithms using applicatives, monads, semirings, and semimodules. It's a pretty big area, and I probably won't be able to cover most of it in this presentation, but rest assured all the details are in the paper. That said, let's get into the main motivating question for this paper, which is how to express search as a monad. By search in this case, we're talking about non-determinism, so that is programs that might have more than one answer for a given question. We're interested in how to construct those programs algebraically, and then how to evaluate those programs, potentially ordering some answers before others according to some arbitrary metric. One such program is this one, which uses the list monad in Haskell to search for Pythagorean triples. The variables x, y, and z here are drawn from the ranges 1 to 10. A guard is used to ensure that they do in fact form a Pythagorean triple, and then that triple is returned. Here's the result on the right. Behind this relatively simple program, there are actually some pretty important theoretical abstractions like the monad and monad plus class, which enable programs like this and have been the subject of huge research in Haskell and functional programming more generally over the past few years. The issue is that this is not the only way to search. In fact, it's not a very good way to search. For one, it's depth first rather than breadth first. So if we wanted to extend the range of the search space from just 1 to 10 to all natural numbers, this would diverge. It wouldn't return any answer. It also doesn't give us any way to order the answers. So if we wanted to search for a certain kind of Pythagorean triple, we just have to do a linear search and there would be no more efficient answer. Now, there is a monad which allows us to do breadth first search. It's been rediscovered a bunch of different times and it's often called a levels monad. We're going to represent it here as a list of bags, where bags are sets that allow duplication. As you can see, it does indeed perform breadth first search. This is the same program searching for Pythagorean triples as the previous one that we had, except that the natural numbers being drawn from are all of the positive natural numbers, not just those in 1 to 10. And you can see on the right here that it does indeed produce a result without diverging. So if depth first search is the free monoid, then what's the levels monad? What about it gives us breadth first search? And that's actually the first question that our paper seeks to answer. We want to give a theoretical and an algebraic background and basis for the levels monad. We want to explain it to the same extent that we understand the list monad. Then we want to generalize this algebra to weighted search. We want to show that the levels monad is actually just a special case of weighted search, and then we want to implement an efficient monad transformer for this generalization. And we want to use this monad transformer to implement algorithms like Dijkstra's algorithm or the Viterbi algorithm and so on. So let's talk about the theoretical basis for the levels monad. This is only a small selection of the background. As I say, it's been studied numerous times. But let's talk about what it does mechanically. Fundamentally, the levels monad does diagonalization of its input, which means that from these two inputs, this is the pattern of pairing that it produces. You can notice that the level of each pair in the output corresponds to the sum of the levels of the pairs in the input. So if you look at 2C here, 2 comes from level 1 using zero-based indexing, and C from level 2, you add those together, you get level 3, which is indeed where 2 is there. If you follow a depth first search pattern, this is the search pattern that you get on the left, whereas the levels follows the one on the right, hence the diagonalization. That pattern of diagonalization is actually the same pattern that you get from polynomial multiplication when you represent polynomials as lists of coefficients. That representation works like this. First of all, you multiply out the polynomial, then you arrange it in order of increasing exponent, filling in the missing exponents, and then those coefficients give you the entries in the list. This is the same, as it happens, as the levels monad when you set the type variable of the levels monad to unit. Because bags of units are isomorphic to the natural numbers, following this isomorphism where the empty bag is 0, single bag is 1, and so on. From this list of coefficients can be translated directly to a levels value, meaning that levels of unit is isomorphic to polynomials. In fact, what's really interesting about this is that the monad plus operations correspond to the polynomial operations. While this is an interesting observation, it's still kind of a superficial one, because while yes, levels of unit is isomorphic to polynomials, we haven't said anything about levels of A in general. In order to do that, it turns out that we'll need some more sophisticated tools, provided by this paper in particular. There, semirings and near semirings are given their categorical analogues, which allows us to show that levels is a polynomial in monad plus, not in the natural numbers, and is a polynomial over bags. That's about as deep as I can go on that topic in the time that I have. The rest of the details are in the paper. Next, let's talk about weighted search. This generalization is going to be pretty simple. The levels monad ordered its search by the exponents on the polynomial that it represented. So to generalize, we clearly have to generalize those exponents from natural numbers to something else. That something else is the subject of this section. We want to figure out an algebra which properly encapsulates the notion of cost on a search. Take this graph, for example. It has 4 nodes, A, B, C, and D, and the cost, or the weight in each path, is X, Y, and Z. The first thing we will want to be able to do is construct new paths by joining all paths together. This tells us that we need a way to combine costs. So it should have a binary operator like this, or this. Secondly, we should know that any node that you're at, you should be able to stay there. There should be a trivial path to that node, and it should have a 0 cost. So these things together tells us that the cost should probably be a monoid. It should also obey some pretty straightforward laws, like for instance, the 0 cost should be cheaper than anything else. Or this one, if it's cheaper to go from B to C than it is to go from B to D, then it should also be cheaper to go from A to C than it is to go from A to D. For our work, we're going to use the Monas algebra to encapsulate costs. It's perhaps a little bit more restrictive than it needs to be, but it covered all of the instances that we wanted it to cover, and the extra laws enabled some optimizations which we're going to use later on. The basis for this algebra is this relation. This is often called the algebraic preorder on monoids. X is less than or equal to y if there exists a k such that x added to k is equal to y. Put it another way, k is the gap between x and y, and if such a gap exists, x is less than or equal to y. We can see straight away that the 2 laws that we had on the previous slide are satisfied by this relation anyway. These are just active proofs of the statements. There's no need to understand them here. They're just here to demonstrate that this is relatively simple to formalize, and indeed it is in our formalization. So this is the definition of monas that we're going to go for. A monas is a commutative monoid such that the relation defined here is both total and antisymmetric. This is what we think of as costs in the paper. Some examples of monases include the natural numbers under addition, rational numbers under addition, and also interestingly probability under multiplication. That last one in particular is what enables us to do things like the Viterbi algorithm. In the paper itself, we actually generalize this further from monases to semirings in general. A monas itself, of course, forms the min plus semiring under some conditions, and it turns out that the search monad is a free semimodule, which means that it doesn't just encapsulate things like the levels monad, but also probability monads and sets and bags and so on. More details about that can be found in the paper, but for now we're going to move on to defining the monad transformer. This is the monad transformer for weighted search that we're going to use to implement Dijkstra's algorithm. We're going to start with a free monad. This is just kind of a shortcut way when you're defining a monad to make sure that it's definitionally law-abiding. So we're going to start with the free monad plus. This is a free monad, but at every level, it's wrapped in a list. Algebraically speaking, this is the free near semiring. From there, we can turn it into a transformer by swapping out the lists with the list transformer. And from here, we can turn it into the heap monad, which is the monad that we're going to use for weighted search, by swapping out the functor for the writer monad. That W there is going to be constrained to be a monas in all of the algorithms that we're going to use it for. The main algorithms that we're interested in working with are graph search algorithms. In order to represent them using this monad, we're going to first need this combinator. This adjoins a weight to a pure value, returning the heap monad. Using this, we can represent graphs as adjacency lists. For instance, this graph on the left with the nodes A, B, C, and D, where the edges have weights in the natural number monas. For instance, the edge from B to D has a weight of 2. That graph is represented on the right there in the graph function, which takes in a node and then returns a heap monad computation of the adjacent nodes, each of them tagged with the weight it took to get there. From here, we can actually implement the cleany star. This should give us transitive closure of a graph. And indeed it does. When implemented directly on the graph above, we see that the transitive closure from A gives us the graph in this diagram here. You see that on the top level, you have the A value itself. Then, under a depth of 3, you have B, which under a subsequent depth of 2, you get to D, and so on. So this is how we represent graphs in the paper. So now we're able to properly describe graphs, and we have a monad that properly describes weighted search over those graphs. The last thing that we need is a way to evaluate those monadic expressions efficiently. And in particular, we need to implement the heap operations on this monad efficiently. The most important heap operation is pop-min, a function which removes and returns the lowest valued element in the heap. In our case, it's going to have this signature, which is a little bit strange because it has a monad wrapping and it returns a list of A's rather than just an A, but it is usable to implement things like Dijkstra's algorithm. The question, though, is can this be implemented efficiently? Remember that we started with a free monad, so everything here is still quite unnormalized and quite unoptimized in form. However, by a kind of a happy coincidence, it turns out that this heap structure that we have here is almost exactly the same as a pairing heap. So much so, in fact, that it's possible to implement the pairing heap merge on this heap structure that we have, meaning that this pop-min-t function can be implemented with the same standard complexity that the pairing heap has. And finally, we're able to implement Dijkstra's algorithm using the search monad. First thing we need to figure out how to do is to cross off nodes that we've seen already so that we don't search from them again, going into an infinite loop. Happily, since the search monad is a monad transformer, we can just layer in a state effect that does that for us. That's exactly what the unique function does. It keeps track of a set of already seen nodes, guards to make sure that the node that it's given isn't in that seen set. If it's not, it updates it, adding it in, and then returns it. Using this, Dijkstra's algorithm is just the following function. While there are a handful of combinators in here that you haven't seen before, they're all very straightforwardly derived from pop-min-t. So that's the end of the talk. There's a bunch more stuff in the paper like hyperfunctions and logic T, which I couldn't even mention here, so do give it a read if you get a chance. In the meantime though, thank you very much for listening.